Okay, sorry. All right, so yeah, I go by Alex. I'm as mentioned, I did my PhD at UC Davis at the Complex Science Center with Jim Crutchfield, and all of the work I'll be talking about here today was done there. But I'm currently at INRIA Bordeaux with Nicholas Brodew, my PI, he's in the back there. And I think I won't get into too much of what we're working on at INRIA during this talk, but Nicholas has a poster on it, and I would really highly recommend coming and checking that out and talking to both of us, because it's even more on the practical side of how do you deal with domain science, how do you deal with real data. What I'll be talking about is much more theoretical. I'll sort of be doing a large overview of computational mechanics, epsilon machines, that basic side of the math, and then some techniques that I worked on as a PhD student, looking at infinite state epsilon machines. So the sort of idea here, this iceberg figure, is that you can have something that looks very simple, like a 3-state object. And so these diagrams, these finite state automata, we think of these as the states, and I'll go through our language and everything. But it looks quite simple here. But underneath, you can have actually quite a complicated system with many correlations, many interesting informational, architectural things going on. And so the question is, how do you tease those out? And then how do you deal with them once you do tease them out? So I've been talking to a few people about the odyssey I've been on. I've been traveling a lot this summer. And a couple people really just requested to see some photos from my last trip, which was in Alaska. So I agreed to, I was like, I have to do that. So just to give some overview on who I am and what I do, I'm trained, my PhD is in physics, and I would put myself somewhere in between math and physics. I'm quite interested in algorithmic information theory, Shannon information theory, dynamical systems, sort of come from a dynamical systems background. But I also just like complex systems in general. So right now, Jim gets on these crazy projects. He's very broad interest. He got really interested in humpback whales recently. So he came to me, I finished my PhD in 21, and it's COVID. And he was like, I was wanting to go work with Nicholas, but I didn't really want to move cross Atlantic during COVID. And Jim was like, I've got some funding to work on this whale communication project. You want to hang out here for another year? Yeah. So that eventually has turned into actually field season. I'm a physicist and I get to do field seasons. But we went up to Alaska and we were doing some recordings of humpback whales. And this is not at all related to my talk, but if you're interested in it, I'm happy to talk about it at other times. One of the main things I was working on, I'll be doing all the math now, getting emails about it this morning. But when I was in Alaska, I was mostly responsible for the fluke shots. This is, called the fluke of the whale, and this is actually how you ID humpbacks, because every fluke is unique. But we also were watching them. One of the main things we were studying or looking at was their peck slapping. So this is a whale that's laying on its back that spins up, and they'll just do this. And we don't know why, but it's very loud. You can hear it from 20 miles away underwater. We also saw a lot of other animals. So we got some nice grizzlies. Our captain caught a sea star, which was returned to the ocean, but also caught a rockfish that was not. So these were some of the fun things we did in Alaska. But it's not at all what I'm talking about, sorry. I'm going to be talking about mathematics and about modeling and about how simplicity can belie complexity. So when I was was at a conference in Telluride, Colorado earlier this summer, and talking to a friend of mine who does a lot of ecological modeling, and he reminded me of this paper by Robert May, where he kind of discusses the very common use of the logistic map in population modeling, and how the logistic map looks very, very simple, and is sort of seen as a simple model to try to describe how populations can grow over time or change over time. But when you look at it from a dynamical systems perspective, you get this chaotic regime, actually, where what these are is a map of the fixed points given R. So as you're sweeping through this parameter, which you might do to try and describe different populations, you can hit a regime you're going through updating R according to some process that you might have, and you might hit something that suddenly is chaotic, and you've got now a chaotic model. You're trying to describe rabbits and Southeast Rockies or whatever. And so Robert May was pointing this out, and that it's important to remember when we are building these models that even very simple mathematical choices can have very strong consequences under the hood. So I was sort of, interested in this because that's often the perspective I'm trying to give, but with stochastic modeling. So this was introduced a bit in our introductory talk. This is sort of a truncated diagram of that figure that you were showing, where I've just taken out sort of the modeling bit because I'll talk about that later. But we imagine that there's some true system underneath, and we have some instrumentation such that we're measuring it, and we get out some string of variables or some string of values that we're measuring. And I'm going to be working in a very theoretical space here. So I'm imagining that this is all, like, we have infinite data. We're assuming that this is all stationary. It's operating according to kind of your basic ergodic theory mathematical assumptions. Loosening those is something that we're working on at INRIA. But my notation here will be random variables as capital letters. So if I'm measuring temperature, my random variable will be capital T. And then the alphabet is how many values it can take on. So let's say that I'm just asking, is it colder or warmer than 50 degrees Fahrenheit? And so I say 0 and 1. The lowercase values will be the actual measurement. So if I say it's hotter one day, colder one day, those are in lowercase. Whereas just the temperature representation would be the uppercase value. And what I'm going to call a process is the full distribution over the bi-infinite string. So I'm measuring the temperature for all time, and I have some distribution over what those strings could look like. So this is sort of imagining like the entire history of the planet, what the distribution of infinite temperatures looks like. So it's a very, very theoretical space that we're imagining. Of course, in reality, you're always going to be working with finite data, and the probability distribution may be shifting over time. So these are things we have to think about when we're working in real domain science. So we've already had a little bit of back and forth about information, and we are very much based in Shannon information theory as well as algorithmic information theory. Start off with Shannon. I'm not sure what the level of familiarity is, but just to explicitly define it, I think something I was thinking about during the discussion earlier is the word information can be quite fraught, as we've already noticed. And I think often it's useful to specify mathematically exactly what we're talking about. So in this case, sometimes people will refer to this quantity as information, but I like to say, okay, this is Shannon entropy, and it's defined according to a distribution. So the actual mathematical term here is that I sum P log P over a random variable. So my random variable in this case, for this plot, is heads and tails. So I'm flipping a coin, and over infinite time, what's the probability of heads versus tails? If the coin is fair, it's 50-50. And so your Shannon entropy is 1 bit. And you could say that that's the amount of information that one learns upon observing the coin flip. So this is that sort of non-intuitive way. It's sort of opposite of how you might expect, because you're thinking, okay, a coin flip is totally non-informative. It's just a random sequence. But the idea is that if I'm flipping a coin, I have no way of predicting what the next value will be. So it's 1 bit of information every time I actually observe it. Whereas if the coin was weighted such that you only ever got tails or only ever got heads, your Shannon entropy is 0 because there's no prediction required. It's just a constant value. I don't need to observe the coin. It's not doing anything for me because I know that it's going to be heads or tails no matter what. Okay, so that's our most basic quantity, Shannon entropy. Oh, and maybe a couple things to note here. This can't be negative, it's positive definite, and that's because, probabilities between 0 and 1, and we're taking the log, and we've got a minus sign out there. So of course, the log of something between 0 and 1 will be negative, but we've flipped that. So just, some mathematical properties that are useful there. And of course, it has this symmetry as well, where 30-70 and 70-30 are actually said to have the same information content if you're thinking about distributions. So this is where that idea of like meaning might come into play, because maybe you care if it's slanted towards heads or tails, but Shannon from entropy doesn't specify that. Okay, so what I'll be using quite heavily is the notation of an information diagram or an eye diagram. And it's sort of drawing an analogy between Shannon information theory and set theory. And so these look like Venn diagrams. And the idea is that if I have some variable here represented by X, there's some amount of Shannon entropy that is associated with the distribution over that variable. And I'm just going to draw a big circle and say that's the amount of entropy associated with that variable. So maybe that's 1 bit, maybe that's 10 bits, maybe it's 0.3 bits. But where it becomes useful is in multivariate situations. So using this eye diagram for a process, what I've done here is I've said, okay, I can think of a process as a string of random variables, right? And so I have the present, which is the variable that's happening at time index now. And then there's a bunch of time indices behind me and time indices in front of me, infinite in both directions. So I'm just going to cluster all of the past and all of the Shannon entropy in the past, put that in one big bubble. I'm going to cluster all of the future and do the same, and then think about the present and do this. And so we imagine in general that some amount of information in the past and the future is shared, right? We imagine that the past influences the future. And so those two things should overlap if I think about their information diagram, because there's mutual information between those two things. The future is not totally independent. If they were totally independent, you would have two bubbles completely separated. And we also imagine that the present interacts with both the future and the past. Some of the present might only depend on the past and not depend on the future, which is this set subtraction idea. And some of the present might be correlated with the future, but have no relationship to the past. So that might be like a random thing where, it doesn't matter what happened in the past, there's some random event, but then it strongly influences the future. There could also be things that are unobservable from just my present measurement, things that matter to the past and to the future, but aren't necessarily observable from a measurement at any given time. Okay. So if I want to think about that entropy that I was talking about, but I want to think about entropy rate. So entropy rate is not just what is how much information do I learn, or how many bits do I resolve when I make a measurement. It's I have a repeated sequence of measurements, and I'm allowed to know everything that I've learned from the infinite past, and then I need to predict the next value. And so in the coin case, it doesn't matter that I know the full past because it's completely independent, identically distributed variable, right? It doesn't matter if I know 10 time steps, 100 time steps, it's still 50-50. So in that case, my entropy rate is identical to my Shannon entropy. But in general, there's some amount of information shared between my present and my past, this slice here, which reduces the Shannon entropy down to an entropy rate, which is this kind of slice moving into the future. And so in general, I think, okay, well, I can learn some amount of information about the structure, the relationships, the correlations going on in my process. And so my entropy rate will be lowered by that knowledge. So oftentimes we're trying to discover the entropy rate because we think of that as the limit of our predictive abilities. We can't do any better than that mathematically. It's impossible to predict beyond that point. Okay. If there's any questions, by the way, I know I'm throwing like a lot of Shannon entropy and stuff, Shannon information theory at people. I just wanted to point out a couple other bits of this information diagram that are worth thinking about. There's the excess entropy, which is sometimes referred to as like a memory or a complexity of a process because it's the amount of information shared between the past and the future. And it actually, if you are calculating the entropy rate by looking further back in time, the excess entropy is the area under the curve there. And so it kind of captures like a sort of how much information do you need to learn in order to get to an entropy rate? How much information, how much structural correlation is there between your past and your future? So you can think of that as kind of a memory, but I would say that that's a bit fraught. So interpretation here can be a little dangerous. And I'll compare the excess entropy to another quantity that's more algorithmic later on in the talk. So notice here, I have not done any algorithms here, right? This is just that Shannon information that was discussed earlier, the first part of that taxonomy. So the other thing I just wanted to draw attention to is this, what we call state information. It's that information I pointed out that's only accessible or not accessible from a measurement at a particular time. And we sometimes use this as a justification for why one models at all. Beyond, we often think, okay, mechanism, interpretation, but I would say even beyond the idea of trying to discover mechanism, there's information that we can't get at that is important to the system that, if you're just taking repeated measurements, you're not going to see. So this information is going to be contained in any kind of model that's optimally predictive. Okay. So let's think about how we construct models of time series. So I'm going back to the coin, my favorite example. And let's say I just observe it, right? And so I'm taking heads and tails and heads and tails, and I do this for some amount of time. And I'm going to sidestep the inference question a bit here. I think, with Nicholas, maybe we can talk about that, during the plenary discussions or during the poster session. But in this talk, I'm sort of just talking about the mathematics of the models themselves. So I'm going to say that given this time series, I do some method to come up with my model. And this is a hidden Markov model. And so I'll just go through all the pieces of this in case there's people in the audience who are not familiar with hidden Markov models. The idea is that your state, which is this circular part of the diagram, is hidden from you. So you don't know what the state is via just observation. I only know whether I saw heads or tails. Now with the coin, it's the most simple example because there's only one state. You can't push a coin into different possible substates of the system because it's just a coin. It doesn't change. And so if you're in one particular state, you have transitions. In this case, because there's just the one state, the transitions have to be to themselves. Where on a transition, I observe a symbol. So every time I flip this coin, I transition here with 1/2 probability of seeing P, 1/2 probability of seeing H. So I could imagine a time series here that goes like my symbols and my states, and it would go, H, T, H, H, T, T. If you've taken a stats course, your professors made you do that, right? But the state would just be 1, 1, 1, 1, 1, 1, because I'm not changing. Okay. So you could have something more interesting, like if you're doing some kind of, this is just an example, obviously, this is not something you would really use, but okay, I'm trying to model the weather in my local neighborhood, and I notice that there's a dry season and a wet season, and when it's wet, it rains 90% of the time, but if it's sunny, it'll be sunny, it'll move into the dry season, and then it will be sunny 90% of the time, but once it rains, I move into the wet season. And so this is a very simplistic model, but you could imagine something like this to try and describe some weather system, and the hidden states are your seasons. You don't know what season you're in, except insofar as you know that if you're observing rain, you must have transitioned into that state. Okay. So the nice thing about hidden Markov models is that if they have certain mathematical properties, you can do information theory directly on them, Shannon information theory. So I'm just going to call it a good model. And this is a good model, a good hidden Markov model. And I can actually just directly calculate the entropy rate by, instead of looking over the full infinite past, I just condition on what state I'm in. So I say, if I'm in state A, I have a P, 1 minus P probability of seeing 0 or 1. So I just go P log 2P plus 1 minus P log 2, 1 minus P. And then I ask, what's the probability of being in A? I'm like in the long infinite time, so maybe it's 2/3. And then the probability of being in B is then 1/3, and it has no entropy contribution because it has a 100% probability of transition back to A. And I just summed that up, and I've got my entropy rate, and I didn't even have to observe the system for an infinite amount of time. So that's great, if I have a model like that. They also have this nice property that so these are I'll go ahead and give the spoiler here. These are epsilon machines that I'm describing. But the states are completely functions of the past, which is to say the information in the state is contained within this bubble of past information. It's not borrowing information from the future, which can happen if you construct a model and you just you're doing ML and you throw, you throw all of your data at it. So, and then you're trying to backdate something, you're trying to predict prior information. You might have a model that includes information from the future. And we don't really want that, right? This is also going to be optimally predictive, which is to say that it carves out that entropy rate there. So none of the information, or it uses all this information that's shared between the past and the present. It's minimal in size, which is to say that bubble could not be made any smaller, and it is unique. So this is the main result of computational mechanics. If you can get at a model like this, it's really, really good. Getting at the model's a little bit difficult, but it's defined in this specific way. So we imagine that we have this space of all possible pasts of your system. So again, the coin, it would be all of the possible by infinite strings, or sorry, just infinite, because you're just thinking about past. So all of the possible sets of H and T and H, T, T, whatever, for your entire system. And you imagine this abstract space that contains all of those infinite strings. And you say, given different pasts, if my prediction over the future is the same, so differences in past have no impact on my prediction, then I would consider those pasts to be equivalent in some way. They're predictably equivalent. And so if I observe that past, or one of the pasts that gives me the same prediction, I group all of them into a causal state. And we say causal because the grouping condition here is predictive. We're saying that the causal relationship between the future and the past for all pasts that exist within this partition is identical. It's equivalent. And the idea here, sort of what information can you throw away with zero loss of predictive utility? Okay. So again, I kind of spoiled because we already had the epsilon machine introduction, but this is doing this construction, and you can kind of imagine already, I think, how difficult this construction might be. But if you do this construction where you carefully account for all possible differences in past behavior that can lead to different predictions, you get to the epsilon machine, which has all of these nice properties. And there was a question, I picked up on some ideas or some thoughts towards the direction of, okay, so I did this, it's optimal in all these mathematical ways. Does that imply that it's capturing mechanism? And I think that's an open question. I would probably fall on the no. I don't think you can make any claims necessarily about mechanism, partially because when I think about the word mechanism, I always get a little bit confused on what it is that we mean when we say mechanism. Gravity, cited as a mechanistic theory in physics, but when we're imagining we just have data and we're trying to understand where it's coming from, it's difficult for me to say okay, is this mechanistic or is it not? But I do think one thing I like to say is that it must be the case that because this model is minimal, that whatever system produced the data that you're observing must be at least as complex as the model that I have learned here. Because if it were any less complex, and I'll say what I mean by complex, if it were any less complex, it would not be able to construct those correlations. It would not be able to produce data that had those correlations. So I think you can kind of rely on this as an Occam's razor type argument. Yeah.
Do you need this? More tightly constrained because it's the only model that.
It's the minimal model that will produce this data, but you could have a larger model, like more states, that will reproduce the same
Oh,
statistics.
yeah, the real one can be more complex.
Exactly. Yeah. So if we believe in Occam's razor argument, we would say, yeah, sure, this must be the real thing. But I don't personally believe that Occam's razor is a universal truth.
Yeah, good.
Yeah. Because I could imagine that there is maybe some more complex thing that actually does describe the system in a more mechanistic way, but then you get into the question of what a mechanism is. So these are things I think would be interesting to talk about. Okay, so when I keep talking about complexity, I keep saying like bigger or smaller. What I mean is this term, we call it the statistical complexity. And again, I argued for, rather than saying information, I argued for saying exactly what mathematical term I mean. What I mean is the Shannon entropy over the distribution of my states. So I have all of these causal states that I've learned. Because this is a stationary thing, there's some stationary distribution, stationary measure over my set of states. So I take the Shannon entropy over that. And that's going to be, you could think of this as like a coding cost for how much space on my hard drive do I need to encode the model that will reproduce the statistics that I have observed. And so that's what I mean when I talk about size. Okay, so the thing is that most HMMs don't have any of these properties that I was talking about. Yes.
And so in this context, computational complexity is of no interest for you. Why?
Well, I think why? I wouldn't say it's of no interest. Do you mean like computational time, like long
How many
time?
bits do you need to revisit to actually, use your epsilon machine and produce the data?
Right. So I'm not sure what that would be capturing that isn't captured by like a coding cost. I mean, because the dynamic is embedded in the stationary distribution. And so if you're trying to understand like what the computational complexity is of a dynamic, I think you can get at that by studying the stationary distribution in the case where you have like an ergodic, nicely stationary thing. If it's non-stationary, then maybe you do need some extra term that is describing like trajectories through the epsilon machine as they're shifting in time or something. But I get like worried about that because even our definitions start to get a little fuzzy. You have to think about conditional stationarity and things like this. But yeah, I think in this case, I mean, we talk about statistical complexity and we say statistical because what our focus is reproducing the statistics that you're observing, because the sort of philosophical underpinning is that you can't do anything other than what you have, right? You have some observation, and unless you somehow have some other insider knowledge, like, oh, I know that this is being produced by a particular code or whatever. If you don't have any information about what the system is other than just your data, you can't go beyond trying to reproduce the statistics when you think about inference.
Alex, just a quick question for clarification. I'm able to understand this very easily from a univariate perspective. Does it easily extend to multivariate, or you're just focusing on the univariate case where X is a univariate?
Right, so multivariate, so you could imagine that you have two processes that are they're simultaneous, and you can think about the joint process, which would then be modeling some kind of multivariate thing if you have 2, 3, 4. You can also think about, I think Alec will talk a bit about transducers, where you're thinking about you have some process that's being transduced or transformed into another process with a different statistical property, and then what are the informational properties of that input-output machine. So these are some of the ways that we think about multivariate, but this is still a pretty open question. A good site would be to also look at Adam Roop's papers, because he's done a lot with space-time rather than just time, which we have here, as well as Nicholas's work has done a lot with incorporating multiple different variables, multiple streams of data.
But you're talking only about the.
I'm talking only about univariate, yeah. Okay, so what my work focused on,
We're also talking about discrete outcomes.
Yes.
How does the world change if you have continuous outcomes?
This is what my postdoc is about. So yeah, we'll talk. I'll talk a little bit about lifting. So right now I've kind of cheated. No one called me out on it. These bubbles are all finite in size because my slide is finite in size. But of course, in general, you would assume that all of these informational quantities diverge because you have infinite pasts. You have potentially all pasts matter, like, so,
But you don't have infinite information about the infinite past.
well, so
You
we'll
have
talk
finite
about,
data in the real world.
we'll talk about informational scaling quantities, which is what I worked on, yeah. Okay, other questions? Okay, so, keep trying to get to this slide. So if you just write down an HMM, like you just write down a set of states with a dynamic over them, most of the time, like with measure of 1, they will not have the property that you can just condition on the states to get your Shannon entropy rate. In order to have that property, the epsilon or the HMM has to have a particular mathematical property we call unifilarity, which is, I'll get to what it is actually in a few slides here. So my question that I was interested in as a PhD student is that given an arbitrary finite state HMM, how would you get to the epsilon machine for it? So I'm sort of already starting with some kind of model in hand, and then I want to think about how I would actually calculate the information theory from it. Okay, so what we're going to do is take our bad HMM and we track what our belief is about what state we're in. So we say, I'm going to start with, because these are hidden states, I'm going to start with a uniform distribution over ABC. I don't have any guess about where I might be in the model. And I'm just going to start observing symbols because that's all I can see. So my observed sequence, lambda, is the null. So I start out in the middle of this simplex, which is representing all possible distributions between A, B, and C. 1/3, 1/3, 1/3 is in the middle. And so the first thing I observe is a 1. And because of the structure of this machine, I can notice that, well, if I saw a 1, I can only be now, or I'm more likely to be in this part of the machine. And so my distribution over possible states shifts a little bit towards the edge. But if I see a 0, because a 0 can only transition into A, we call that synchronizing. And so now I know for sure that I was in A, and I put a dot up there. And if I see another 1, I know I must be in B, so I put a dot down there. And then if I see another 1, now I've lost my certainty, because from B, I could have transitioned to myself, or I could have transitioned to C. And so I've lost certainty about where I was in the machine. And this is what we call non-unifilarity, the ability to lose track of where you are in your model, even though I'm keeping track of the observations. And this is the property that prevents you from doing the Shannon information theory directly on this machine. Yes.
As you do this, are you assuming you do not know the transition probability?
You do know them. So you have this model, you know it, but you don't know where you were in it.
Okay.
Yeah. And so what we say is that if I were to just do this for infinite amount of time and I'll fill in this simplex, what I build up is a set of what we call belief states, because they're beliefs over where you are in the machine. And what these look like generically is they're fractals. So each of these squares is one of those simplices for a different underlying model. So I've got a bunch of different HMMs here, and I track each of them over a long period of time, and I get out these different state distributions. And so what this is telling me, like, imagine that these were all just flat over the triangle. What that would tell me is that I can never really have a better or worse guess about where I am in the machine when I'm observing things. But if I have something like this, where it's very sparse, what this is telling me is that I'm always like pretty sure that I'm in B or A or C. I'm not 100% sure because I'm not right on the corner, but I'm always like in that 90% zone. So the more sparse this is, the closer it is to being a 3-state thing. So we call these sets of belief states the infinite epsilon machine, because it turns out, and this is what we worked on for several years, it turns out that you can actually use those belief states as causal states. So those become now the states of my machine. So each of these little blue dots now represents one of those black circles that I was showing earlier. But of course I can't draw those black circles because this is fractal infinite thing. And so some of the math behind this is these are the attractors of what are known as infinite iterative function systems, which might be familiar if you've ever looked at like fractals or computer graphics, especially early on. It was very common to use iterative function systems in order to generate fractal images, which then were used in the earliest computer graphics. Yeah.
does the fractional dimension of this fractal tell you how close you are
Okay,
to
I'm gonna stop you. We'll get there. So there's like some mathematical machinery here about existence and uniqueness that is contained within the papers.
But is there any fundamental difference between this and IFS?
Yes, because we specifically, the IFS, I would say, is the type of mathematical system this is. But in order for it to be one of these infinite epsilon machines, I have to start with a finite state HMM that's well connected, that, you know, has real probabilities. Okay. So for most finitely generated hidden Markov processes, this is what the epsilon machine actually looks like. So some of our papers, if you've read the papers from the Crutchfield group, will have pictures of epsilon machines that are, you know, 2-state things, 3-state things, and they look very pretty. And those are the ones that are easy to work with. So we often work with those. But if you're thinking about the full space of processes, even just the space of hidden Markov processes, most of the time you're in this infinite state zone, which is really a lot harder to work with. And that's not even, you know, including processes that are further up the complexity tree. So we're sort of arguing here that even a very simple thing can give you a complicated model if you're married to ideas of optimality. So how do you calculate the Shannon entropy rate from something like this? Because remember, that was sort of the whole goal of like working with these models in the first place. So David Blackwell actually answered this question in a different context way back in the 50s. He was trying to calculate entropy of functions of finite state Markov chains, which essentially this is what a hidden Markov model is. It's a function of a Markov chain. And what he showed is that given a measure over a fractal-like set of predictive features, you can take the integral over that and get the Shannon entropy rate. What he did not say is how to get that measure. So what we showed is that you can generate this measure given that you have these underlying well-connected Markov models by just taking very long realizations of this belief update system. And so you can take a long enough time series and get arbitrarily close to the entropy rate. So statistical complexity, that structural term that I introduced about like the memory or the coding cost of a model. In this case, well, this is a fractal set. So if I try to take the Shannon entropy rate over it, it will diverge in general. So what we do is the fractal dimension or the information dimension, actually, because we're taking into account the measure over the state set. So fractal dimension, I'm not sure, again, what the level of familiarity is in the room, but in general, we think of the fractal dimension or the fractal multispectrum as values that represent a scaling property of a data set. So you have, if you imagine that I have some instrument, like a telescope or a microscope, and I can slide the instrument to be finer or coarser grained, and at each of those graining, each of these settings, I measure what I'm observing, and then I plot, you know, I say, you know, here's my setting on my microscope, and here is how complicated my set looks like at that setting. And it looks in general more complicated as you know, go finer grained, but for, you know, given mathematical conditions, there should be this linear regime. And so what we define as the information dimension is the slope of this curve. So we say, okay, basically, how much more complicated is it getting as I'm taking more into account? And the steeper it is, sort of the higher the information dimension is, the more details are contributing to your, like the more details are adding to your complexity costs. If this was totally flat, it wouldn't matter what value you are observing at. So what we showed, what I showed is that, in fact, this information dimension done on this geometric object is the same as the divergence rate of the statistical complexity. So we define this quantity of the statistical complexity at different fine grainings. We could define the slope of that as the statistical complexity dimension, which is equal to the information dimension of this set. So this is pretty in the weeds. I want to talk a little bit about how we actually calculated this. Turns out calculating fractal dimension is pretty tough. So information dimension even more difficult because you need to get a sense of what the measure of this object is. So the classic way to do it is box counting dimension, where you put a grid over this with size epsilon, and you literally just slide through a grid of different resolutions and estimate what the measure is at each size, and then you plot this point by point. But that method has a lot of instabilities to it, so we wanted to look around and find something a little bit more pleasing to our dynamical systems preferences. So what we found was, or what we ended up landing on, was the Kaplan-York conjecture, which says that if you calculate the Lyapunov spectrum of a dynamical system, you can relate that through this kind of weird calculation to the information dimension. So again, I'm not sure levels of familiarity, so I'll quickly discuss what the Lyapunov spectrum is. If you think about some trajectory, like this is Lorentz, of course, and we imagine some trajectory in 3 dimensions traveling like this, and the trajectory, the tractor is going to be being pulled and squished in various directions. So the wings are being flattened down into their respective planes, but they're also being pulled out this way. As you have that constant push and pull, which is very characteristic of chaotic systems. And the Lyapunov spectrum, what it does is gives you the amount of stretching and contraction in orthogonal basis directions. So in this case, for the Lyapunov or for the Lorentz system, we have 3 different values because you have one for each dimension or that you're in. And then once you have this spectrum, you do this very weird thing where you sum up your Lyapunov exponents from most positive, increasingly towards 0, and then start adding the negative ones in, up until if you added the next negative Lyapunov exponent, the whole sum would tip over into being negative. You stop one before, and then you divide by that next most negative one. And then you add the index. And so this sounds really strange, but the heuristic way to think about this is that if you are adding up these Lyapunov exponents, up until the point that the contraction tips over, or sorry, the expansion tips over into being contraction, the point at which you stop doing that is sort of the point at which the system stops filling space. So that index is the dimensionality that your attractor is going to live in, because that's how many dimensions this system is able to push trajectories out into. So that's your integer value. And then this extra little bit is sort of the leftover expansion that goes beyond that next dimension. And so it's a little bit of a strange thing, but it works really well. And Lai-Sang Young and Lejapier proved this in the 80s with a series of very, very mathematical papers. I recommend, of course, reading the physicist paper because it's a little bit more readable. Sorry if there are mathematicians in the room. So the Lorentz attractor, the example you have here, you've got one positive Lyapunov exponent, one 0, and one negative. And so the Lyapunov dimension, you do this calculation, 2.0. So this thing is a little bit more than 2-dimensional.
How close is it to the actual fractal dimension if you compute? I mean,
It's accurate. It's equal for various mathematical constraints that Lejapier and Young lay out. It has to be an axiom A system. They say that it's for typical dynamical systems. So it will be exact, but of course you have to calculate Lyapunov exponents exactly as well. Okay, so the issue that we had, and I'll sort of run through this quickly because this is pretty specific to what we wanted to do, but the issue that we had with applying the information dimension just out of hand, the Kaplan-York conjecture, that it was designed for the deterministic systems, right? The Lorentz is a deterministic system. And what we were interested in were these stochastic systems. Hidden Markov models are stochastic, and iterative function systems are stochastic. So we needed to have a way to adjust this formulation for stochasticity. And so what I ended up doing was introducing a new quantity that I call the ambiguity rate. So if we go back and we think about the entropy rate again, we imagine we're in some state and we're looking out into the future, And we're thinking, okay, if I see this symbol, I'll move to this state. If I see that symbol, I'll move to that state. You can imagine this branching set of futures out before you, right? And the spreading of those futures is captured by the entropy rate, because the entropy rate is telling you, if it were 0, there's only one choice forward. If it's 1, it's 50-50. They're telling you how much your probability is getting smeared out in time. Now, the ambiguity rate, I think of as something of a dual, which is that if I'm in a state, I think to myself, where did I come from? What were my past trajectories that brought me to this location? And the uncertainty in that set of this tree that could have brought me to my location is my ambiguity rate. So if you imagine that you're moving through this state space, and in this case, I really want to think about it geometrically rather than just the 3-state thing. You're flowing through state space and you're looking forward, and there's almost a light cone out in front of you of all the places you could end up. And there's also this light cone out behind you of all the places you could have come from. And those two things are sort of squishing and contracting and expanding as you're going through in time. And the balance between those two things, my certainty in where I came from and my uncertainty in where I'm going, contributes very heavily to what the geometric property of the attractor will look like. So that was the insight that we had. And it ended up being pretty simple mathematically. And so to be fair, this is a conjecture. We haven't proved this formally mathematically, but we have a nice set of numerical results and heuristic, very physicist arguments for why you can essentially treat this quantity as another Lyapunov exponent. So it ends up modifying the entropy rate, because the entropy rate is your uncertainty moving forward, but it's got to be conditioned by this uncertainty in the reverse direction. And then this ends up being our formula for statistical complexity dimension. Yes.
So the K in this case is the value at which H mu minus A plus the sum of the Lyapunov exponents
Tips over.
tips over.
Yeah. So your K also gets slightly redefined in that way.
So will this dimension be different from what would be an equivalent dimension from an IFS?
No. So right now in the literature, before we introduced this, there was no way to, so this is a bit in the weeds, but if you think about a simplex and you think about, let's say I have an IFS with two functions and the image of those functions does not overlap. In this case, we could calculate the dimension. So that's actually what we did in our first paper. We just said, ignore any IFS where there are overlaps in the images of their functions. But there was no way to calculate the case where you had these images that overlap, because if you think about it, if I'm in a belief state here, what the overlap, what that means is that this map could have mapped me here, or this map could have mapped me here. So there's some uncertainty in my past. And realizing that that was what was messing up, like no one could calculate the dimension in this case because of that particular property, and said, well, if you compute that and then subtract it off, it actually corrects for this overlap. But it is if you were to do box counting and you were able to get an accurate, like exact value from box counting, it will come out to the same value.
So in preparing for this workshop, I learned you can learn about the dissipative nature of a system if you go backward and forward through a Markov chain and just compare the two entropy production rates.
Oh, interesting.
And so I wonder if you would go through your system now forward and backward and calculate your statistical complexity dimension from the forward and backward.
Right.
What would that tell us? Would it also tell us about the dissipative nature of the system? Yeah,
very potentially. This is something I'm very interested in. Actually, my recent work has been a lot in reversal, because if you so if you have this nice mathematical like stationarity, all of these things, we know that entropy rate is the same in the reverse and forward direction. So if I run a system forward, the entropy rate is 2.3 bits. If I run it backwards, the entropy rate is 2.3 bits. But the ambiguity rate is not equivalent in the forward and reverse, because the ambiguity rate depends on building a model of your system, because it's the model of the system that allows for uncertainty. Because if I if I know my full trajectory, I don't have any uncertainty, but if I know I'm in a causal state, there's potentially multiple paths that could be contained in that causal state. But if I build my causal states in the forward direction and I build my causal states in the reverse direction, those sets are not the same. So there is some irreversibility with how much we have to fuzz out the past, depending on if we're going forward or reverse. And I do suspect that there's thermodynamic consequence. Alec might want to talk on that more.
So I believe the results that you're referring to come from like Crookes detailed fluctuation theorems that say the entropy is the log probability or the log ratio of the probability of the forward trajectory and a reverse trajectory. And that's a very common way of like looking at non-equilibrium steady states and trying to extract like how much energy is being wasted. But the thing is, with these sorts of processes, they can be totally irreversible, but they can have the same complexity in the forward and reverse time direction. And so I think the statistical complexity, or often called causal irreversibility, right, it is sort of a different measure of time's arrow, which is sort of independent of this assumption. So people use these things to these measures of dissipation to look at a video and say which is the direction in which time is flowing. And I think statistical complexity, causal asymmetry represents a different, maybe even more compelling measure in some cases. So it's related, but a little bit.
Yeah, because it doesn't favor energetically. Well, I don't know. That's an interesting question. Thinking about energetics of it, if you were.
There are energetic considerations, and what I'll talk about. This causal irreversibility basically tells you how energetically accessible the information is, depending on how it's read, like the direction and time you read it.
Which for me, from a practical perspective, would help to say how predictable is my system and how quickly will it either explode or move to a very boring state.
Okay, so the main result that I want to emphasize here is that we now are able to calculate both randomness in terms of entropy rate, as well as structure in terms of this statistical complexity dimension, even for processes that require infinitely many causal states. So what I think, like, sometimes the ambiguity rate, I'm throwing a new term out, it can be a little bit confusing. And what I like to think about in terms of the ambiguity rate is not so much in on its own, but rather this difference between the entropy rate and the ambiguity rate, because you can think of that as a model growth, in the sense that if you have a finite state model, your entropy rate and your ambiguity rate will be equivalent, and so the difference between them will be zero. And we can think about this because I have 3 states over time, and if I'm in any given state, I look forward and there's a branching pathway of things that could happen, and that's my entropy rate, but it can only contain these 3 states. And if I look backwards, there's these branching pathways of where I came from, but it can also only contain these 3 states. I can't visit any new areas in my system because I just have these 3 states. And there's no like C prime that I'm transitioning to at any point. Yeah.
Is the 3-state system the minimum number of states that you're required? You can do it with 2 states.
You do it with 1. You can have the coin example that I showed earlier, that was just a 1-state epsilon machine. Yeah. And so this object, because of course, if you think about this like embedded in the simplex, it would just be 1 point here, 1 point here, 1 point here, 3 points. The dimension of a 3-point thing like that is 0, right? The dimension of a point is 0. So it makes sense that this comes out to 0 because then my Lyapunov, Kaplan-York conjecture also comes out to 0. Now, on the other hand, something that might have been in the back of people's minds thinking about this talk is, what about the case where every single history counts? Like, you can do this causal state construction, and it sounds very nice to say, like, oh, well, 2 histories don't make a difference. But in general, most of the time, every single history will make a predictive difference in a physical system. And in that case, your ambiguity rate is actually 0, because there is no uncertainty about where you came from. And you imagine this fractal branching tree, and your growth rate of your model is at the rate of an entropy. So it's kind of like you didn't do any better than just measuring every value, except for the fact that you now have this geometric understanding of how those histories cluster. So maybe you had to calculate every single history, but some of those histories are totally geometrically absent from your representation of your system. And so your statistical complexity allows you to understand that, even though, yes, it's true, you had to calculate every history, the same as the process next door, but they have some different geometrical properties. In general, though, things exist in this middle range where some history, some subset of histories can be grouped together and some cannot, but you still have an infinite, uncountably infinite set of causal states. And this is the area I'm very interested in, because I think this is the most typical area. There are some distant differences that don't matter, but there are potentially infinitely many differences that do matter. And being able to tease out which is which is one of the most fundamental questions in trying to do this optimally predictive modeling. So that regime is what I'm currently most interested in looking at. All right, so I will give my acknowledgements. So of course, obviously, Jim Crutchfield, I have to thank him for my PhD, being my PhD advisor, but also, of course, Alec, Adam Roop, I mentioned earlier, Sam Loomis, who's in my same cohort as me, as well as Nicholas, who's in the back there at Inrian now. So thank you all for your attention.
We're taking a lot of questions already about, but another 5 minutes. Going to question. Okay. So to the point made earlier about this is some finite states, and you kind of gave some examples. Maybe one was hot or cold, and that kind of defines your granularity of what you're measuring. Mm-hmm. If you were to start saying, okay, so I have a set of data, I'm going to partition it hot, cold, do this analysis, and then say maybe hot, cold, medium, do this analysis, and keep bumping up your sort of dimension, and you have some model that sort of would aggregate down, so it's sort of self-consistent, and you look at I'm getting fuzzy in what my question is, but
well, I think what you're kind of describing is this idea of the scaling, like the informational scaling. So this is something that I think is very difficult when we think about information, because there is no, so thermodynamically, maybe you can argue for this, but at least when you're thinking about a measuring tool, there's no intrinsic scale, because you can say hot and cold, you can say hot, medium, cold, or you can do it by degrees, Fahrenheit, Celsius, Kelvin, right? And you can kind of keep building up a new, like newly refined tools or newly refined alphabets. And one thing that I'm interested in thinking about is, rather than saying, okay, we have to select one as the most correct, we slide through our instrumentation and look at how the complexity of our inferred model changes. And that like dimensional property is more intrinsic than just any particular scale. Hope that answered your question.
One more question. Yeah, thanks for your talk. So I have one question, and it seems like, right, that if you kind of stick with kind of enforcing optimality or like minimality of your model, then kind of the price you pay is like infinite dimensions.
Yeah.
Or like infinite states somehow that you can visit. And I mean, I am not like somehow into this. Like I don't have a lot of background knowledge, but it seems like that somehow having infinite states also might be an issue for some.
Well, yeah, because your computer is going to get mad.
And I wonder if there's like, I don't know, a kind of way of viewing it and saying, okay, maybe I give up optimality, or I try to like loosen this in some way, and then I kind of stick to, or I get finite amount of states.
Yeah, absolutely.
Like a trade-off that's made.
So I didn't even touch on this, but actually this work was initiated by Sarah Marzin, who's now at the Claremont Colleges. And she originally imagined this dimensional quantity not as an intrinsic informational property of the underlying system, but rather a rate distortion guide on how, we recognize we can't work with an infinite state model, So we say instead scale through, your coarse graining, look at this slope, which is your dimension, and call that a rate distortion. Because it's kind of intuitive, right? The higher the dimension is, the more variability matters. And so if your dimension is very low, like I'm, again, I said that this was, if I have just 3 points here, it's a 0-dimensional thing. If I have clusters of points here, maybe I'm like 0.2 dimensions. Well, if it's 0.2, I can pretty much approximate that with very little loss as a finite dimensional thing. And so one value of this quantity is to tell you how much you can get away with finitization, and also how you should finitize, because the geometry of embedding your states puts more predictably equivalent states closer together.
I think that's one of the.
Thank you so much for your talk. I really enjoyed it. Also, your emphasis on mathematical rigor in notation. I think that is something very important. Yeah, so I didn't want to ask this question, but then I wondered, now I saw this at the end. So your iceberg, right? This one, you did physics, right? So I think this is physically not correct.
The iceberg?
Yes.
Yeah.
Because I believe more than 90% should be underwater, right?
Yeah, you're correct.
Okay.
This is a limitation of ticks. I'm gonna blame ticks.
Yes. Maybe